Everything in the universe spins: planets, stars, galaxies, and even the particles inside your atoms. I know how that sounds. Like I'm saying the cosmos is literally one giant rotating machine. But when I say everything spins, I don't mean everything is rotating in the same simple mechanical way. I mean something deeper. Nature treats angular momentum like an almost sacred accounting rule. Once it shows up, it's astonishingly hard to erase. And in a little while, this will take us somewhere unexpected, because the place where angular momentum gets its most extreme stress test is not a galaxy or a solar system. It's a black hole. And black holes don't just challenge our intuition about gravity, they challenge our intuition about information, and maybe about what space even is. Before we earn that conclusion, we need to clear the ground. First, what this is not a claim that the universe as a whole is globally rotating like a record. On the largest scales, observations show the universe is very close to uniform and isotropic, and any overall cosmic rotation appears tightly constrained. So if you came here expecting a single axis the entire universe is spinning around, that's not where we're going. Instead, we're talking about something local and universal. All over the universe, structures form through collapse, collisions, mergers, and turbulence. And in all of those messy processes, angular momentum behaves like a currency that can be exchanged, but not simply deleted. You can transfer it from one body to another. You can redistribute it between orbit and spin. You can radiate some of it away through gravitational waves or electromagnetic radiation in special situations. But the total bookkeeping is relentlessly consistent. Nature keeps the books. That's why rotation keeps reappearing, even when no one asks for it. Now, here's an open question to hold on to as we go. If angular momentum is just a quantity, why does it feel so fundamental? Why is it conserved so stubbornly that it shapes everything from the largest structures in the cosmos down to the quantum behavior of particles? We'll come back to that. But first, we need intuition. Picture a figure skater. Arms extended, they spin at a steady pace. Then they pull their arms in, and suddenly they spin faster. It feels like a trick, like the skater found extra rotation from nowhere. But nothing mystical happened. The skater didn't create new spin, they rearranged their mass. The same angular momentum is now concentrated into a smaller configuration, and the rotation rate increases to keep the accounting consistent. This is the first crucial idea. When systems shrink, tiny twists become loud. Now scale that up. A cloud of gas in space begins to collapse under gravity. Real clouds are not perfectly still. They are turbulent. They're being tugged by nearby structures. They have chaotic motion eddies, collisions, pressure waves. Even if the overall cloud is only slightly biased toward one direction of swirl, collapse magnifies the consequences. As the cloud contracts, that small initial twist becomes a faster and faster rotation. Matter that might have fallen straight inward instead gets organized into a spinning disk. Not because disks are magically preferred, but because disks are a natural compromise between inflow and conservation. A disk is what happens when material tries to move inward, while angular momentum refuses to disappear. If we want a more everyday image, imagine a busy roundabout viewed from above. Cars approach from different streets at different angles. It's messy, but the geometry of the roundabout forces the mess into a clean circulation. The roundabout doesn't inject spin into the cars. It constrains the flow in a way that naturally produces a loop. Gravity does something similar. It doesn't create angular momentum out of nothing, but it amplifies and organizes whatever angular momentum is present because shrinking a system makes the same conserved quantity more visible. That explains why spin is so common in astronomy. Planets rotate because the material that formed them collapsed and accreted. Stars rotate for the same reason. Many galaxies rotate because they grew from merging and collapsing matter with a net angular momentum budget, and that budget didn't go away. But we still haven't hit the strangest part, because the word spin also appears in quantum physics, and quantum spin is not just a small object rotating. If you try to picture an electron as a tiny spinning ball, the picture breaks. It breaks so badly that if it were literally a spinning sphere, parts of it would have to move faster than light. So here's open question number 2. Why does quantum theory use the same language, angular momentum, for something that is not classical rotation at all? To answer that, we need to talk about the difference between the map and the territory. Temperature is a useful example. A weather map shows temperature in colors, red for hot, blue for cold. But temperature is not a substance painted onto the air. It's a summary of microscopic motion. It's what we call the average energetic jiggling of trillions of molecules. Temperature is real. It's measurable. It can cook food, power turbines, and drive storms. But it's not fundamental in the sense that you can point to one molecule and say, that molecule has exactly 72 degrees Fahrenheit inside it. Temperature is an emergent description of deeper dynamics. Spin, at least, the way it shows up across physics, often has that same character. It's a dashboard indicator for deeper constraints. Sometimes it corresponds to visible rotation. Sometimes it corresponds to something more abstract, how a system state responds when you rotate your point of view. And that phrase, rotate your point of view, is doing more work than it seems. Because angular momentum is tied to a symmetry of the laws of nature, rotational symmetry. If the fundamental rules don't care which direction you point your experiment, then there is a corresponding conserved quantity. We don't need equations to feel the point. Imagine living in a universe where the laws of physics changed slightly when you faced north versus south. In that universe, turning something around would not be a harmless relabeling. It would change what outcomes are possible. Rotational symmetry would be broken, and the conservation of angular momentum, as we know it, would not hold in the same way. But our universe seems to have rotational symmetry extraordinarily deeply built in. So angular momentum is not just a convenient quantity, it's the physical shadow of a symmetry that appears to be woven into the rules themselves. That's the bridge between the skater and the electron. In quantum mechanics, spin is not a little object twirling. It's a built-in kind of angular momentum, an intrinsic label for how a quantum state transforms under rotations. Rotate the apparatus, and the state responds in a specific, rule-governed way. That response is quantized, it comes in discrete packages, and the world keeps that accounting as faithfully as it keeps energy. So now we can partially close open question number 2. Quantum spin uses the language of angular momentum because it is angular momentum, just not the classical picture of spinning matter. It's symmetry made physical. But we still haven't answered the title-level question. Why does it show up everywhere? Why does the universe keep turning this particular dial? For that, we need to go where conservation laws become more than common sense. We need to go to the sharp edge of physics, black holes. Black holes form when matter collapses so intensely that an event horizon appears, a boundary in space-time beyond which signals can't escape to the outside universe. Once something crosses the horizon, it can't send a message back out. From far away, the object becomes hidden behind a one-way surface, and black holes are strange not only because they trap matter, but because they seem to erase detail. Take a complicated object, a star, with layered composition, magnetic fields, turbulence, and internal structure. Let it collapse into a black hole. From the outside, after the black hole settles down, it can be described by a small set of numbers, mass, electric charge, and angular momentum. That simplicity is unsettling. Where do the details go? Where did the story go? This question becomes explosive when we remember that black holes are not perfectly black. Quantum effects near the horizon cause them to emit radiation, Hawking radiation. Over immense timescales, a black hole can evaporate. Now we have a tension that has driven decades of research. Quantum mechanics strongly suggests that information is not fundamentally destroyed. If you start with a well-defined quantum state and evolve it forward in time, the evolution is supposed to preserve information. It can scramble it, hide it in correlations, spread it out in complicated ways, but not delete it. Yet Hawking radiation looks thermal, like heat, like static. It doesn't obviously carry the detailed imprint of what fell in. If a black hole forms from complicated matter and later evaporates into what looks like featureless thermal radiation, where did the information go? This is not just philosophical discomfort, it's a consistency problem. If information truly disappears, then quantum theory would need rewriting in a deep way, and here's where angular momentum re-enters the story with force. Black holes do not merely absorb matter. They absorb conserved quantities. If matter falls in with angular momentum, the black hole becomes a spinning black hole. That spin affects the geometry around it in measurable ways. In fact, near a spinning black hole, space-time is dragged around a phenomenon called frame dragging. The spin doesn't just sit there as a number on a label, it changes what time and space mean near the horizon. There are regions where nothing can remain at rest relative to distant stars because space-time itself is being pulled into the rotation. So angular momentum is still being tracked even in this extreme regime where our ordinary intuitions fail. It survives collapse. It survives collapsins. It survives the conversion of matter into geometry. Now here's open question number 3, and it's the one that will take us up the final ladder. If black holes seem to hide information but still faithfully advertise conserved quantities like spin from the outside, what does that tell us about where information is stored and how it's organized? To approach that, we need one of the most surprising established facts in theoretical physics. Black holes have entropy. Entropy is a measure of hidden possibilities, the number of microscopic configurations that can look identical at the macroscopic level. For ordinary systems, entropy typically scales with volume. More space means more ways to arrange microscopic details, but black holes are different. The entropy of a black hole scales with the area of its event horizon, not the volume of its interior. Area, not volume. That single fact is one of the loudest hints we have that our everyday picture of space might not be the whole story. Because if entropy is, in a sense, a measure of information capacity, how many distinct microstates can hide behind the same macroscopic appearance, then black holes suggest that the maximum information you can pack into a region is limited by its boundary surface, not by how much room there is inside. Let that sink in slowly. Because it's easy to hear it as just a technical detail, but it's more like a crack in the foundation of the classical picture. If the information content of a region scales like the area of its boundary, then perhaps the deepest description of what happens inside a region can be encoded on its surface. This is the seed of the holographic principle. Now, when people hear holographic, they often jump to the idea that reality is fake, like a projection. That's not what physicists mean here. Holography, in this context, is not an insult to reality. It's a claim about how reality can be described. Two different descriptions can be equivalent. One can look like a world with gravity and a volume of space. Another can look like a quantum system living on a boundary. Both can describe the same physics, with no loss of truth, just different languages. Think of a song again. The song can be represented as vibrations in air, as digital data, or as notes on a page. The representation changes. The content doesn't. Holography suggests that space-time geometry might be a representation and emergent interface of deeper quantum information living in a different form. And now, finally, we can connect the black hole's spin to something even deeper. If black hole entropy is tied to the horizon area, then the horizon behaves like a kind of information-bearing surface. Not necessarily in the sense of tiny tiles with letters on them, but in the sense that the fundamental counting of states seems to live there. So what does it mean for that surface to carry angular momentum? For the information bearing itself to have a twist that changes space-time around it? It suggests that spin might be as fundamental as the information storage itself. That it's not merely a motion of matter through space, but a structural feature of how the underlying degrees of freedom are organized. At this point, we need to be careful. The holographic principle is strongly motivated by black hole physics, but the most explicit, mathematically controlled examples come from specific kinds of model universes. This is where a famous proof of concept enters. In the late 1990s, physicists discovered a remarkable duality often called ADES-CFT. Here's the intuition first version. There exist toy universes in which a gravitational theory in a higher dimensional spacetime is exactly equivalent to a quantum theory without gravity living on the boundary of that spacetime. Same physics, two descriptions, a dictionary between them. In that framework, black holes in the gravitational bulk correspond to hot, strongly interacting quantum systems on the boundary. And spinning black holes correspond to boundary systems carrying angular momentum. So on one side, spin looks like rotating space-time geometry frame dragging. Twisted light paths, horizons with rotational structure. On the other side, spin looks like a conserved quantity in a quantum system that doesn't even have gravity in its formulation. That's a profound lesson, even if our universe is not literally the same space-time geometry used in those models. A-DESIFT is not a proven direct description of our cosmos, but it shows something crucial. Holography can be exact in consistent physical models. It's not just metaphor, it's not just philosophy. It's a working example of a world where geometry emerges from something more abstract. And if that's possible, then it becomes reasonable, though still not settled, to ask whether our own spacetime might also be emergent in some way. This brings us back to emergence, and we should say it plainly. Emergent does not mean unreal. Temperature is emergent and real. Pressure is emergent and real. A wave in the ocean is emergent and real. A wave in the ocean is emergent and real. You can surf it. You can measure it. You can drown in it. But it isn't a fundamental particle. It's a collective behavior. If space-time is emergent, it would still be real in the sense that it governs how rulers measure distance and how clocks measure time. It would still be the reliable stage of our everyday experience. The claim would simply be that the deepest description, the one that resolves paradoxes and explains black hole information, might be written in different variables. Now let's bring spin back into focus one last time, with this emergent perspective in mind. In classical physics, angular momentum is tied to rotation in space, an object spinning or an object orbiting. But in quantum physics, spin is intrinsic, a built-in property of a particle's state. It doesn't require a little rotating object. It requires a certain transformation rule under rotations. So here's a possible unifying view. Angular momentum is not merely about things moving through space. It's about how physical states behave under the symmetry of rotation, about what remains invariant when you change orientation. And that symmetry is so deep that it may survive translation between descriptions. Whether you describe the world as geometry in a volume or as quantum information on a boundary, angular momentum remains a meaningful conserved currency. Now we can close open question number 1, the one we started with. Why does angular momentum feel so fundamental? Because it's not a random feature. It's tied to a symmetry of the laws themselves. As long as the rules don't care about absolute orientation, there is a conserved quantity that keeps score. And because the universe forms structures through collapse and interaction, that conserved quantity gets amplified, organized, and made visible everywhere. That's the practical answer to why everything spins. But there's still a deeper, more speculative possibility that black holes invite us to consider. If black hole entropy scales with area, and if holography is telling us that the deepest accounting of information may live on boundaries, then the geometry we call space might be a derived interface. In that case, what we call rotation in space may itself be an emergent concept, an effective way of speaking about deeper transformations in the underlying description. This does not mean we've proven that space-time is emergent in our universe. It means the clues are strong enough that serious physicists keep following them. So what do we take away without exaggeration? 3 implications, 2 solid, 1 more tentative. First, established, collapse amplifies twist. Perfect symmetry is rare. Small imbalances in motion become large rotations as systems shrink. That's why we see rotation in star formation, planet formation, accretion disks, and galactic structure. The universe is dynamic and messy, and conservation laws make the mess coherent. Second, established. Quantum spin is not a tiny spinning ball. It's angular momentum in the quantum sense, discrete, intrinsic, and tied to symmetry. The word spin is historical, but the physics is precise. It's about how states transform under rotations, not about little spheres twirling. Third, more speculative but motivated, spin may be a clue about what remains fundamental when we go deeper than spacetime. If holographic ideas capture something true about gravity and information, then conserved quantities like angular momentum might be more primitive than the geometric picture we draw in our minds. In that view, the universe spins everywhere because angular momentum is a stable, conserved structure that survives across levels of description, classical and quantum, bulk and boundary, geometry and information. Now let's return to the everyday universe and answer a question that often comes up. Where did the initial angular momentum come from in the first place? In practice, it comes from the fact that the universe is not perfectly smooth. Tiny fluctuations, random motions, tidal torques from nearby matter mergers and interactions seed angular momentum everywhere. When structures form hierarchically small things merging into bigger things, angular momentum is exchanged and redistributed, but the total budget remains meaningful. Over cosmic time, this produces a universe filled with rotating systems. So the universe doesn't need a single global spin. Local spin is enough. And once local spin exists, gravity makes it hard to ignore. At this point, it's worth pausing on the emotional texture of the idea, because it's easy to miss what's strange here. Rotation is not just a detail of astrophysics, it's a recurring theme across scales. And black holes tell us that this theme survives in a regime where matter becomes geometry, where horizons appear, where information becomes a physical problem, and where the maximum information content of a region seems to be written on a surface. That's why this question is not just why do planets rotate, it's why does the universe keep such careful track of twist? Because twist, in physics, is not merely motion. It's structure, it's symmetry, it's conservation. It's an accounting rule that reality refuses to abandon. So let's recap the ladder we climbed. We started with a provocative observation. Spin is everywhere. Then we clarified it. Not global rotation of the universe, but the near-universal appearance of angular momentum in real systems. We built intuition with skaters in collapsing gas. Shrink a system and the same angular momentum becomes faster, more obvious spin. We saw why disks are common. They're a natural structure that allows infall while respecting conservation. We stepped into quantum physics and acknowledged the surprise. Quantum spin is not classical rotation, but it is still angular momentum symmetry made physical. Then we went to black holes, where conservation meets the event horizon. Black holes radiate, they evaporate, they create an information puzzle that forces us to ask where information is stored. And we encountered a hard, established clue. Black hole entropy scales with area, not volume. That points to holography, the possibility that the deepest description of a region is encoded on its boundary. We looked at a proof of concept, where holography is exact in specific models, a duality where gravity in a volume corresponds to quantum information on a boundary, and where even something as dramatic as a spinning black hole can be translated into a boundary system carrying angular momentum. Finally, we used emergence carefully. Emergent doesn't mean unreal. It means derived. Space could be like temperature real and measurable, but not the most fundamental language. And that brings us back to the title. Maybe the universe isn't made of things that spin in the simplest sense. Maybe the universe is made of rules that keep score. Rules built from symmetry. Rules built from conservation. Rules built from information that refuses to be destroyed, even by horizons. If you want more videos like this slow, conceptual physics with no equations, subscribe. And if you're still here, I'd like to leave you with one question to answer in the comments. If space-time is emergent, what do you think is more fundamental, geometry or information? And where do you think spin belongs in that hierarchy? Because the unsettling possibility is this. The universe may not be a collection of spinning objects. It may be a ledger, and spin may be one of the deepest entries that never gets erased.